All right, we're looking at combined transformations today. In other words, you put two or more transformations together. First thing we need to kind of examine is, does the order that you do those two transformations in matter or not? So, to do this, we're going to use this graphing software, our online graphing software, Desmos, and we have this crazy function here that's essentially an absolute value function that's limited in between -1 and 3, just to keep things small and simple so we can track what's happening more easily. We're calling that f of x. All right, so that's going to be our base function. Now, how we're going to combine transformations is we're going to create two new functions here. The first one we'll call g of x, and we'll make that a transformation of f of x. The first thing we'll do is we'll do a horizontal reflection, which we do that by replacing x with negative x. If I had just gone g of x equals f of x, it's exactly the same, but I want this. Now I'm going to make that a different color too so we can see what's happening. So that's our horizontal reflection, reflected about the y-axis. That's our first transformation. Our second transformation here is we will transform that new one, g of x. Now we'll make another one called h of x, and we're going to make that a transformation of g of x. So this is going to be, let's do a vertical expansion on that. So instead of h of x equals g of x, we're going to make it 2g of x, and we get that black one there. That's our final transformed graph. You start with this basic function, you do the horizontal reflection, you do the vertical expansion, and you get to this area here. Right now, the question that that we're asking here right now is, if you change the order that you do those two in, do you end up with the same result or not? All right, so let's do it in the reverse order. Instead of f of x being that and g of x being that, we'll do the vertical expansion first. All right, so there's the vertical expansion. Now let's keep our first step as purple, and then let's take that g of x and now let's reflect that horizontally. All right. Now, if you remember, that is exactly where the previous one ended up. It ends up in that exact spot. The first way we had it set up, it gets reflected over the y-axis. Okay, horizontal reflection. The orange one got reflected to there, and then it got stretched vertically. Here, you stretch it vertically and reflect it over. It doesn't make a difference. One of these changes the x values. One of them changes the y values. It doesn't make a difference. Now let's try one other, and you can see what I mean here. We'll start with that same base function. We're going to do two transformations in the same direction this time. That one was one vertical and one horizontal, so it makes sense that that there's no difference whichever way you do it, because they're affecting different coordinates. So here, let's do that's going to give us a horizontal expansion. Right? Horizontal expansion. Now, this is on right now. That's why that's black, right? This one, we haven't graphed it yet. So that's horizontal expansion by a factor of 2 when you replace x with a half x. And then we're going to take that function and I'll transform it like this. Okay, we'll put that on. You get a horizontal expansion, and then it gets reflected over to here. So maybe just track one point here. Let's track what happens to this point. Okay, this point is, oops, we don't want that. We want to, we can see what the coordinates are, 3, 2. That point goes to 6, 2, which is off the screen. It's okay. And then it gets reflected over to negative 6, 2. All right. If we change the order of that, well, let's look at one other point first. Let's look at where this vertex is. This point was at 1, negative 2. When you expand it horizontally by 2, it goes to 2, negative 2, and then it gets reflected over to negative 2, negative 2. If you change the order of that, think about what's going to happen. First, you're going to do a reflection. That point would get reflected over to there. And then second, it's going to get expanded out to there. You're going to find that this order doesn't matter either. Okay, so if we get rid of that, and we get rid of this negative sign here, do it the opposite way. First we do the horizontal expansion, then we do the horizontal reflection. Right, it's just as we thought for that point. That gets reflected to there and then expanded. This point gets reflected to there, and then the distance doubles. You end up in the same spot. Okay, the graph ends up in the same spot. Now these are both in the same direction. They're both horizontal. And let's just for this, let's do the same thing just for the sake of completeness with a vertical. We're going to do a horizontal or vertical compression there, and then let's do another. Let's take that one and expand it. Okay, so we've done two stretches, right? We've taken the original orange one, compressed it down by a factor of a half. It's been vertically compressed by a factor of a half, and then that graph has been expanded vertically by a factor of 3. If you reverse those, so if we do the vertical expansion by a factor of 3, it's way off the screen, but now if we're going to do the half here, that's the same spot we were in before, okay? That final graph. Intermediate step's different, but doesn't matter the order that those two happen in, two stretches. All right, now let's think about some of the algebra behind this, why this may work here. So we need some more space here. And the first set of changes we made, we did I'm just going to put horizontal reflection, and we did a vertical expansion by a factor of 2. We started with y equals, so let's do it in that order, and then we'll do it in the reverse order, and we'll see what we end up with here. So we started with y equals f of x. We then took that and we did the horizontal reflection. So we got f of negative x. That was our first change we made. Keep this out of the way. And then we did the vertical expansion. Vertical expansion, we could put the 2 out in front like that, or we could have put it on the other side, but we'll stick with this side for today. Now, so we end up with this as our final function that we got. If we did it the other way, or in other words, if we started with y equals f of x, and then we did the vertical expansion times 2, and then we did the horizontal reflection, see the difference that we get, if any. Now we thought we shouldn't have a difference, so the algebra should work the same as well. 2f of x, and then if you make the change in here, right, there's no difference between those two things. Right, you end up either way getting with that. That's your final function. Now when we were graphing it, we were using two other functions as intermediate, or as intermediate steps on that, or to see one step at a time. These are the same. Okay? If you have a reflection and an expansion, in fact, if you have any two transformations, if one's horizontal and one's vertical, it's not going to make a difference, right? Because one's going to be a change inside that function and one's going to be a change outside that function, right? It's not going to make a difference which way you do switching the order of these two things, the way we did over here, okay? Two transformations in different directions. Two transformations in different directions. Order doesn't matter. Order doesn't matter. All right. And next one we did was we did in the same direction. We did a reflection and an expansion again. So that time we did. Let's start with our y equals f of x that we did. We did a horizontal expansion times 2. So we changed this to f of a half x. And then next we did we took that thing and we took that thing and did a horizontal reflection. So what we got to do now is at first we replaced x with a half x, right? This x up here turned into a half x. Now what we have to do is take this x and turn it into, replace it with negative x. So I'm going to put the negative x there. Anytime you replace it with that negative, you should probably have another set of brackets there just to make sure. So that x became negative x. Now the simplest way to write that, first of all, I should just keep track of this here, horizontal reflection. The simplest way to write that is f of a half times negative x is just going to be negative 1/2 x, right? Basically both those things are multiplying things, it's not going to matter. And just to confirm that, we're going to look over here. If you do it in the reverse order, so if you do this first horizontal reflection, you have, we're going to replace that x with negative x on the first change here, like that. And then the second change we're going to make is our other transformation, horizontal expansion times 2. So in this case, we got to now change that x to a half x. But that negative's still there, right? So when you end up with something there, it doesn't make a difference, right? These are the same. That's the same as that. All right, so that order doesn't matter there too. This was reflection and a stretch, or in other words, expansion, compression. Expansion, compression in same direction. Now that's just one example, but you'll find that any two you combine aren't going to make a difference. Okay, expansion, compression, and a reflection in the same direction. Order still doesn't matter. All right. We did do a vertical one too, but you'll find that that works exactly the same way. As long as it's reflection, expansion, compression. Any reflections, expansions, compressions, all in the same direction. Reflections, expansions, compressions. Combining these, order doesn't matter. Okay, in any order yields same result. Now, the thing, that's a bit before what I wanted to get to there. Didn't leave myself enough space. The last thing that we need to think about is the one type of transformation we haven't looked at here is the translations, right? When you're adding something. These things all up here involve multiplication. Translations involve addition, right? Translations you're gonna find involve addition. Okay, these are all multiplication, right? You're multiplying by a number in the coordinates. This is an addition type thing. Okay, and you're gonna find something different here. Now for this, when we involve a translation, we're gonna do it in the we're gonna do things differently. First, we're gonna look at the algebra, and then we'll go to the graph to see what we have. All right. So let's just consider doing these two things. Let's consider doing a horizontal compression by a half, and let's combine that with a horizontal translation of 3 to the right. Okay, and let's combine those in two different orders. So the first order is going to be that order that I put right there. And the second order is going to be take those things and do them this way. First do the translation, and then do the compression. If we start with a function here, again, just y equals f of x. If on this side over here, let's make myself a little more space here. I can do a little bit of a horizontal compression on these words here to give myself some more space, because I think we can still read them there. And let's just, to keep things straight here, let's make it a different color too. How about orange? Okay. If we're going to if we're going to over here do the horizontal compression first. Horizontal compression, we have to take the x and replace it with 2x. Okay, that achieves our horizontal compression. So we took this and replaced it with that. That was this. Okay, that change achieved that. If we want to now cause this change, if we want to go to the right by 3, you have to take the x and replace it with x minus 3. But you need to put it in some brackets there, and then the rest we're going to leave just the same. Okay, so what we got there, I'll rewrite it here just so we have it without that highlighting on it. F of 2 x minus 3. When you replace a single variable like that with a binomial, you need to add that extra set of brackets in there. So that's the function that we get. Now the other way around here, if we start f of x and we change this to f of x minus 3, because we're first doing the translation here. So first we're replacing x with x minus 3 to cause that to happen. Now we're going to do the other one here. Now we're going to replace this x with 2x. Now here we don't have brackets around that 2x. You could put them if you really wanted to. You could put an extra set around that, but you don't need them if the next thing's a minus there, because multiplication is going to happen before that anyway. So let's fix that up. Oops. And we get that, right? This is y equals f of 2x minus 3. Now, if you look carefully, these are different, right? Probably, when you learned working with how to work with polynomials and expanding, you'd notice that this expression here, that is different than that, right? Writing 2x minus 3 is different than writing 2x minus 3. Those are different. If this was written without that set of brackets inside, it'd be 2x minus 6. All right? This is going to affect, the order is going to affect things here. We can do that just by tracking one single point here and just doing those two sets of transformations here. All right, these two things. If we do our two transformations now, let's take that and bring it down here and put it right here. Okay, if we do those two transformations, just track a point here. Let's track 4, 6. Okay. If we do those two things, if we do our horizontal compression by a half, that point is going to go to 2, 6, right? Horizontal compression. And then if we go 3 to the right, that point is going to go to 5, 6, right? Because you made that change twice. This got cut in half, and then you went 3, you added 3 to go 3 up. If we do it in the reverse order, so this was this. If we do it in the reverse order, which was the other way around, which I guess we can just do it without writing it again. If we start with 4, 6, if we do our 3 to the right first, that point is going to go to 7, 6, right? That point goes to 7, 6, 4 goes to 7. If we did this first, that was our 3 to the right. I should keep this color coordinated there. And then if we took that point and now did a horizontal compression by a half, this is going to go to 3.5. It's definitely different, right? It ends up in a different spot. If you first of all do the translation and then you compress it after that, you end up compressing the translation. If you do the translation afterwards, you don't end up compressing it. This went 3 to the right, and then it stayed 3 to the right from this point here. Right? When you compress it, you took this value and compressed it. You cut that in half. Whereas here we added 3 to it to do that translation first. Then when you cut it in half, that translation gets cut in half as well, so it's going to end up in a different spot. Let's confirm that just by looking at the graph and doing the same sort of thing here. Okay, so if you make this f of x here, get rid of that, and we'll get rid of this before we go too much further. So our 2 there we were doing was we were putting a 2 in there. That compresses us horizontally. And then we were going to go 3 to the right. Let's look carefully where that ends up. Right, this point is at 3.5. Right? Let's say the vertex is at 3.5. Let's watch where it ends up the other way around, because we have predicted here that it should make a difference. If we do this first, minus 3, and then here we do the 2. Okay, where does that final graph end up? Down here, right? Now that's in a different spot. It was here before, right? All right. You start with this orange graph. You go 3 to the right here. So that point, every point on the graph, to get to the orange to the purple, 3 to the right. And then when you compress it, this point gets compressed, right? This is 4 units, so it gets cut in half, 2 units, right? This point up here that was 6 units goes to 3 units, right? When you do the expansion or compression afterwards, it's changing, it's compressing the shift that you did, right? It's only like you're not that full 3 units away. So, important thing to take from this is if you do a translation and an expansion compression. Let's give ourselves the full screen here to write on. Combining translation with an expansion. Expansion, compression, and if we did the same thing, we didn't do a reflection here, but it's going to be true for that as well. Not a T, a reflection, it's going to be the same thing. Order matters, all right? Anytime you involve a translation with one of the other ones. And again, the simplest way to think of it is, this is an addition thing. These are multiplication or division things. And when you combine those things that way, just think of a number, right? If you take a number like 12, if you do 2 operations to it, divide by 4, add 3. If you do those things in the reverse order, it's going to make a difference, right? Now let's actually try that here, right? If you divide this by 4, you get, if you take this number, I'll just write it. If you take that number, divide it by 4, you get 3, obviously. And then if you add 3 to that, you get 6. Whereas if you do it in the reverse order, you start with 12, but then you do this one first. You add 3, you get 15. If you divide by 4 there, what do you get? 3.75, right? You're dividing the chunk that you added as well. Different things. Now, that is important to remember to keep things simple here. What people end up doing is if you look back at the way we had those 2 functions written out, they're written in 2 different ways here. Probably the simplest thing to do is to remember and think about how you'd make the changes to get to where you are. Most of the time, functions end up being written out in this form with that extra set of brackets in there. If it's written in that form, the translation has to come last. If you happen to write it in this form, well, you could just think about it that, well, the translation has to come first there. Or your other option could be to just change it into the form that you like. All right, change it into this form with 2 brackets, and that's probably the safest thing to do, to change it, right, if it's not in that form. So you could take this one and write that expression inside there, which we'll highlight again so you can almost not even see it anymore. If you were to write that with an extra set of brackets in there, it would be 2. If you factor that 2x minus 3, it's the same as 2x minus 1.5, right? Now, if you were to graph that, you'd find that that would give you the same thing. you can write that inside part like that instead. Okay, that part, let's see if we can see it there. 2x minus 3 is the same as 2x minus 1.5. Okay, and if you graph both of those, you'll find that they are the same. All right. Now, this is turning out to be quite a long video, but this is a pretty involved concept here to think about. Okay, if we were to graph, no, not if we were to graph. Let's not do that right now. I'll actually do this in two parts. At this point, we're hopefully okay with the idea that if you do an expansion, oops, let's make some more space here first. If you do a reflection, expansion, compression, all of those things, doesn't matter how you switch it around, right? Because you could do, if you're doing an expansion or a compression, you did the reflection after that, even if it was in a different direction or the same direction, you can switch these things around and the order's not going to matter, all right? So, like that could be last or whatever. The thing that is going to matter is this translation. So if you do the translations, the simplest thing to do is if you have a function that is in this standard form, as in you have some number times f, and you have some other number, and you have x plus or minus, whichever way you want to write it in here, h, this is sort of our standard form. If it's written in this standard form, this is the order that those translations, or that those transformations happen in. If it's written in that form with that two sets of brackets inside there, right? Where that inside expression is factored. It happens in this. All of these happen first, and then the translations happen last. Okay? Some people like acronyms, and they remember this CERT. If you were that type of person, you want an acronym to remember, you're welcome to do that, as long as you realize that the first three doesn't matter, right? If it's written in some other form that doesn't have that inside expression factored, like if you write 3f 2x minus 6 plus 7 or something like that, you can't just do this translation last the way it is, because it's not in the right order. Now you could do what we did, which was that translation can happen before that compression, but a lot of people find it simpler to just kind of go through and think that I want it in that form before I do anything with it. So they would change this, again, and change this expression inside there and write that expression as instead 2x minus 3, factor it out. Those two things are going to give you exactly the same, right? If you took something and did those two changes with it, which you'll see right now, we'll just pick a point here and do it. All right, let's pick 12, 24. So we're going to do these two. This is we have two things involved there. This one is a horizontal compression by a half, and then if it's written in that order, right? If this bracket's in there, then we have a horizontal translation, 3 to the right. Up here we have, and this has to be in that reverse order, right? This is horizontal translation of 6 to the right, and then followed by that is a horizontal compression by a half. If you're to do both those sets to this point here, you see that you'll get the same thing. So let's try that. We'll do this one first. Well, if you do that horizontal compression, this is going to go to 6, 24, and then we go 3 to the right, we get 9, 24. Okay, we'll do the red one now over here. If we start at 12, 24, and then first we go 6 to the right, where do we get to? We get to 18, 24, right? And then we do our horizontal compression afterwards. You get cut in half, 9, 24. You get to the same point. No matter what point we started with, we'd find that's true. As long as you know the order, how the structure of the equation affects the order, you should get the same point. All right? But the simplest thing I think for most people is to know that order, when you have this factored form, translations come last. All right? That is a long video, but it's a pretty complicated topic. All right? Now there's going to be some practice and some examples of going from the graph to the equation and equation to graph in part 2 of this very long topic. All right? Thanks for listening this long.